morning. I'm very happy to be here today. But before we start, I would like to all of you to answer one question. How many of you are currently living in an apartment building? Great. And how many of you are ever faced any water crisis or any kind of a crisis in that building? Yeah. Well, isn't it chaotic? Yes. Well, let me tell you another type of a chaos that I'm going to talk about today that happens in a managed or unmanaged MDU networks deployments, which is what I'm covering today. The RF chaos in dense deployments such as MDUs. Before I go into technical, I would like to share a small personal story. When I was younger, I used to talk in the groups. One-on-one conversation were easy, 3 or 4 people were also quite manageable. But as the group become larger, things become difficult. This is because everyone is trying to talk at the same time. And it becomes chaotic. Now let me tell you, this is exactly what happens in the dense Wi-Fi deployments such as MDUs. Okay, so this is exactly the building where I'm currently living. It's a classic example of unmanaged MDU. So what happens here is every tenant, they have a choice to select what ISP providers they want to choose. And here everyone has their own Wi-Fi router. So what I did was, just a second. Okay. Okay, so what I did was, I did a quick scan. And as we all know, in such scenarios, 2.4G band is always congested. So that's what it happened. 7 SSIDs I found in 2.4G band, out of which 5 SSIDs were having a very good signal strength. And in case of 5G band, I realized that some of the SSIDs are using channel 36 80 megahertz bandwidth. And when I looked into my router was also configured at channel 36 80 megahertz bandwidth. Now I have total 10 Wi-Fi clients in my home. All are contending for the medium access with my access point. But with this scenario, they have to also contend with the neighboring devices in the deployment. So how do Wi-Fi access points or devices in general contend for the medium? That Wi-Fi uses CSMA CA, unlike Ethernet. And let me tell you this with a simple example that we all already know. There are 2 stations in my scenario, 1 AP. All the devices will first start with the random backoff counter. And in this case, station 1 will achieve the medium first. Once it achieves the medium, station 2 will go into CCA busy state. And AP will ACK that data. So that time period, the station 2 will be completely busy. It will hold the backoff counter and it cannot transmit anything. After this, the station 2 will continue its backoff counter, and station 1 will also restart its backoff counter from some random number. And in this case, if my station 2 has some data to transmit, it will transmit and station 1 will go into busy. Now these are just 2 stations. Imagine I have 10 clients. And imagine if you have a lot of clients in the MDU deployments, like in the dense deployments such as MDUs. And this becomes even worse when we have a scenario which is like a collision, hidden node problem. Here we have CTS and RTS mechanism where stations have to make themselves more, they cannot access the medium more. So they have to wait for longer time. Now imagine this scenario with 200 apartments in a building with almost like 2,000 devices in the entire deployment. This becomes very chaotic. And this is because actually, let's say you have more access points than you have non-overlapping channels, then some of the access points may need to use the frequency. Again, this is called as frequency reuse. And in this case, we want to avoid overlapping, but we also want to have more number of channels. So clearly, if you have wider bandwidth in the deployment, such as 80 megahertz or 160 megahertz, this will cause more problem. So you need to have more channel availability, more number of channels with non-overlapping. You need to reduce the bandwidth. And if you have higher bandwidth and you have a higher transmit power, that will also complement it more. And eventually what happens is in dense MDUs, many devices content for the medium, so backoff freezes more often. And this reduces the transmit opportunities for the clients. In case of scenario where collision is detected, because it's a dense deployment, higher error rate will happen. In this case also, the contention window will rise in case of collision detection. So then again, this is a problem. There's another problem where, let's say you have group of clients with different diversity of transmit rate. So let's say your station 1 is a lower fire rate, station 2 is a higher fire rate. Even though my station 2 can achieve better with his fire rate, because station 1 is taking more airtime due to its lower fire rate, station 2 will get lesser opportunity in that medium. So throughput is clearly not just your fire rate. It also depends on others' airtime occupancy. So what is the impact? Impact is your optimal good put is not just depending on your payload. It also depends on total airtime, not just yours, but others' airtime. It consists of many parameters, as you can see here, and we all know about this. So how to solve the problem? You know, we have many, we have discussed about the main problem. So clearly the problem is airtime. And many of these airtime variables, let's try to look one by one. One of them is management frames, where we can reduce the lowest possible basic rate and supported rate from the management and frames from 1 Mbps and 2 Mbps to 5.5 Mbps. Now here is one observation I did with beacon overhead calculator, that I have one radio with 4 SSIDs and the beacon interval is 100 millisecond. So what happens if I use 1 Mbps in 2.4G band, the airtime occupied by the beacons are 9.10% overall. But if I change it to 5.5 Mbps, you can see clearly the beacon overhead was reduced to 2.39%. So this can give some value. Next, we can reduce the beacon overhead by introducing the MBSSID. So what happens is in classical, access point deployments where you have multiple SSIDs, let's say in this case we have 3 BSSIDs. These 3 BSSIDs will have their individual beacon frames. So let's say you have 100 millisecond of beacon interval. In a 1 second, you will end up having 30 beacons. And for every probe request, you will have 3 probe responses, 1 from each BSSID. With the introduction of MBSSID, what we can do is, clearly, we can have a transmitted BSSID and non-transmitted BSSID. Transmitted BSSID can package the non-transmitted BSSID data, or such as whatever its capabilities and so on, into that, and you will end up having 10 beacons per second. Because non-transmitted BSSIDs information will be available in the transmitted BSSIDs. And also for the probe response, you will only get 1 probe response for 1 probe request. We can also reduce the overhead by reducing the number of SSIDs itself, right? Why not reducing the number of SSIDs? So that's how we can come up with the multi-pre-shared key concept, where each SSID can have multiple pre-shared keys, and we can allocate these pre-shared keys to different type of users and groups. And we can also have these users and groups part of a different VLAN segment, so that each apartment or each unit can have their own private network. But one of the thing is 11AX also introduced a feature called BSS coloring and spatial reuse operation. So imagine in a scenario where you have to use the channel again, but you cannot plan it in such a way that you want to keep it in a distance where it does not overlap. Sometimes it will overlap. Like in my scenario I showed you, it was overlapping. What will we do? In this scenario, what happens is, in my station A is currently connected to AP1, but it is also able to see the AP2, but with the very poor RSSI, not, let's say, some minimal RSSI between -62 to -82 or something around that. So 11AX provides a feature called BSS coloring, where you can configure the BSS color information into the HE operation element in the frame, and then you can configure the BSS color, partial BSS color, and BSS color enabled or disabled option. What will happen eventually is, you have a station A, it will detect the transmission from in the medium from various stations. If the station B in this case is an intra BSS transmission, if it is able to detect any transmission from intra BSS, it will first look whether it is my color or not. If it is my color, which means it's intra BSS, it will do the regular CSMA CA. But if it is not my color, if it's some other color, which means some other BSS, it can still do transmission, but with some configuration threshold values which can be configured. And that is properly defined in BSS coloring and spatial reuse operation parameters. What else we can do? You know, OFDMA, preamble puncturing, and MU-MIMO. These are one of the things we have heard a lot. So what happens is, OFDMA actually adds a benefit to reduce latencies in the denser deployment scenarios. What it does, it subdivides the Wi-Fi channel into smaller frequency allocations, which we call as resource units. By partitioning the channel, parallel transmission of smaller frames to multiple users occurs simultaneously. For example, a traditional 20 megahertz channel can be divided into as many as 9 smaller subchannels. Now, using OFDMA, a Wi-Fi 6 AP could simultaneously transmit small frames into 9 Wi-Fi 6 to the 9 Wi-Fi 6 clients. And you know, preamble puncturing adds an extra benefit, because what the preamble puncturing does is it provides a clear preamble puncturing, in preamble puncturing, devices perform clear channel assessment on every 20 megahertz sub-channel, and it adapts the transmit bandwidth based on that. So preamble puncturing takes advantage of downlink multi-user OFDMA to avoid transmission in the busy secondary sub-channels by not allocating resource units to that portion, to those positions, basically. Sorry. And in case of scenario where my devices say that, hey, I want the full bandwidth, I don't want these smaller segments. That's where you know, MU-MIMO comes into the picture. It says, why should everyone wait, right? I have multiple antennas. I can create multiple spatial streams simultaneously. So while OFDMA divides frequency, MU-MIMO divides space. But you know what? In dense deployments, OFDMA delivers generally more consistent gains than MU-MIMO. Because many devices generate small bursty traffic, which will benefit from efficient frequency scheduling. MU-MIMO shines when there are multiple simultaneous high throughput flows. Now, we can do more optimizations. Now, you can have a 6G adoption. Like in 6G, you will get more channels. You will get lesser noise. TWT, because you know, in case of IoT heavy MDU deployments, what happens is you can have you can use this feature target wait time, where you can make this IoT devices to use less airtime. And you know, 11 kVR, where we can do a lot of optimization. See, static channel planning is one thing, but nowadays everyone is using advanced RRM algorithms, where you want to have your capabilities to be understood by RRM algorithms, and they optimize the network dynamically. Now, band steering and load balancing, you all know that we can do like, we can move the clients which are capable for 5G and 6G to the, so that we can reduce the contention from the 2.4G band. We can do frame aggregation by introducing AM-PDU and AM-SDU aggregation, but I would suggest not do a lot of AM-SDU aggregation in the high error rate environment such as this. Block CAC, client isolation, and multicast to unicast conversion, I will tell you about this. So these optimization require a fully managed MDU, because you know, in case of unmanaged MDU deployments, the problem is everyone will have different device, everyone will have different management interface, right? So we need a proper fully managed MDU where one person or one optimization can control the entire network. Now, but this also comes with some challenges, okay? So what are the challenges? So, you know, like one of the challenges I found was that, let's say I was talking about airtime, right? In all the presentation, right? We want to improve our airtime, but airtime is not just coming from the Wi-Fi data packets. It also comes from the service discovery packet. I was in a hotel, right? And in hotel, what I did was I opened my YouTube app and I wanted to cast my YouTube screen to the TV. When I opened that cast thing, I was able to see 10 or 20 TVs in a list. And all those 10 or 20 TVs were having same name. So how would I know which TV is mine? I called their IT person and they said they cannot fix it. They don't know how to fix it. Okay, this is by default. Now, this is one of the problems that comes in a managed MDU where the proper network segmentation is not done and you are not assigning per VLAN thing for each room. Now, in case of MDUs also, similar problem can happen because service discovery is one of the challenge that modern MDU want to solve. So what happens is, it can become a significant overhead. Technologies like AirPlay, Chromecast, and smart home devices, they rely on MDNS, which uses multicast. Without optimization, such discovery packets are flooded across the local network. A Bonjour gateway learns and caches available services, allowing it to answer discovery requests or selectively forward them. This is one of the solutions that we can do. So basically what happens is, if I want to discover a device and I will say, hey, I want to look for the devices, then whoever is the device, they will respond back. But in case of, if we have a proper MDU in deployment, we have a Bonjour gateway or MDNS gateway, that packet will be received to the AP and AP will already having that information that what are those devices. And then only those devices will be converted to as a unicast. So whatever the TV or any devices which want to send the MDNS response, that response will only come back. So all the requests will not flood to all the devices basically. That is one of the problems. Second thing is, see, with multi-PSK, or we can segment different apartment units into different VLANs and so on. But you know what? You are just segmenting on wireless side. What about if I have an AP in my open area and there is a wired port open? Any user can go and connect their device on the wired port. So we also need a wired port isolation. That can be achieved by MAC authentication based scenarios. So there are there are many solutions to solve these kind of problems, but these are the kind of a thing. So what happens? What is the good MDU architecture? A good MDU architecture, first you enable 6 gigahertz if possible. Okay. Second thing is you give multi-PSK or dynamic PSK, or you also can have, if you have a better budget, you can also host a radius server-based authentication. And you can have different VLANs for each apartment so that they are isolated in the network. All the guest SSIDs or guest network, you only keep it to the ground floor because guests will generally come to that. So it depends on each scenario. If you are a hotel, if you are an apartment building, different types of scenarios will happen. They require different types of solutions. You can have, as I said, MDNS Bonjour gateway. That is one of the solution to have it. So yeah, MDU is not like regular residential deployment. It requires proper planning. It requires a lot of optimizations on top of it, and it also requires good hardware, because you cannot go into ISP providers and they provide you a regular hardware, and with that regular hardware you are able to achieve such level of optimizations. So yeah, MDU requires a good design. Thank you.
Thanks, Shivam. I think you've given a minute to us. So I think open to questions. I think there are mic runners. Please raise your hand. Mic will reach you. I think Chetan has a question.
Thank you, Shivam, for the presentation. So between enterprise and residential is where this MDU may be sitting in terms of the topology usage. I just wanted to understand in terms of security, in terms of the clientele, what differences did you observe between residential versus MDU versus enterprise?
So I would say, like, in case of residential, no one actually cares about security. No one actually cares about, they all, let's say as an Indian, like we want to cover about our cost. We want a cheapest option, right? We don't want we want a low budget option. So what ISP, we only want to have our ISP provider to provide the router. Optimizations on top of it, as a regular user, I would not be able to manage it. Now, I don't know why my Wi-Fi is not working properly. In case of dense deployments, this is a problem. So we need a between semi-managed or fully managed kind of a scenario based on the apartment setting, because there is no such strong rule that how you want to deploy a MDU. You can have a managed, depending on how user wants. You can customize it accordingly. So yeah, optimization done on top of it, like enterprise require high level of securities, lot of tunneling features and so on. Here we just want a simple Wi-Fi without introducing RF chaos and without introducing networking problems.
Any further questions? We do have time for one more question. Anybody? Yeah, Vishnu, can somebody get a mic to Vishnu?
Yeah, I sure. So you talked about all the problems which actually can happen in MDU, which is very good. So when we are moving towards Wi-Fi 7 to Wi-Fi 8, so what kind of improvements can we bring from this 7 and 8 perspective? Maybe Srikanth can also help answer. Or,
Yeah, so maybe I will explain, then you can add on top of it. So in Wi-Fi 7, currently, if you see, the number of devices adoption is one of the things. So for example, if you see IoT devices, such as IoT devices, now they are moving to 6G capable devices in the new developments, but existing deployments are still using legacy clients. So in case of Wi-Fi 7, it can bring improvements in case of 6 gig adoption. If we have 6 gig, because it has more frequencies, we can adopt that. That's the only one thing that I see. And also in Wi-Fi 8, we have multi-device coordination, which can also bring a significant improvement in MDU, but we have to see how features are delivering when we see the real action in the field from Wi-Fi 8. You want to add?
Okay, thanks, Shivam, for kicking us off. Yeah.